Welcome back. We're going to talk now about the quadratic formula, which might feel like deja vu. We already did discuss this in Module 1, but it's an extremely important part of the CLEP, so we're going to look at it again, specifically in the context of solving quadratic polynomials. So let's review. One way to solve a quadratic equation is somehow formulaically. So if I'm interested in solving this, ax squared plus bx plus c equals 0, then I can get my roots, right? So these are my solutions, aka roots, simply by plugging into this formula. Now, this sort of is interesting because it illustrates the case in which we'll have distinct roots and which we'll have repeated roots. So we saw in the previous submodule that we can have repeated roots, and that happens precisely as indicated by the formula. If this thing here is 0, this is sometimes called the discriminant, then you'll get exactly one root. Otherwise, you get a plus minus something, which is how you typically get the two roots for quadratics. So the formula, I think, really tells you even more than just how to find the roots of a given polynomial. It tells you sort of what the general structure of them are. It tells you when you'll have repeated roots, when you'll have distinct roots, and how the distinct roots will be different. So I think it's a very beautiful formula. Let's look at some applications of it. So something kind of standard, x squared minus x plus 2 equals 0. We would like to solve this. We could try factoring it. We can also use the quadratic formula. I think in this case it's not obvious how to factor it. And in fact, I think you could spend a very long time trying to figure it out because the roots are not real. They are complex numbers. So we'll sort of give some indication for this before giving a fuller exposition of complex numbers in Module 4. But we do need to kind of experience them a little bit right now. So if we plug into the quadratic formula, we get x is equal to a is 1, b is negative 1, c is 2. So I get x is negative b, so 1, plus or minus square root of negative 1 squared, minus 4 times 1 times 2, divided by 2a, 2 times 1. So 1 plus or minus square root of 1 squared, minus 1 squared is 1. 4 times 1 times 2 is 8, so minus 8, divided by 2. So I get 1 plus or minus the square root of negative 7 over 2. So I think this is a little strange, right? We have the square root of a negative number here. So this is exactly what leads us into the study of imaginary and complex numbers, is when you have a quadratic formula that doesn't have real solutions, when you have the square root of a negative number incorporated. So this is what's called a complex number. And we can write it as, and this is sort of the most canonical way to do it, 1 plus or minus square root of 7 times I over 2, where I is the square root of minus 1. And this is our first foray into imaginary numbers. I don't want to say too much more about them. It's a whole submodule in Module 4, and it's just a huge field of mathematics talking about imaginary and complex numbers. But now we know that they can come up even in sort of elementary examples. So let's look at one more quadratic. Let's look at 2x squared plus 3x equals 4. So on the face of it, this doesn't really fit the quadratic formula, right? The quadratic formula would say I need to have some quadratic function equals 0. Here I have a quadratic function on the left, but then it equals some non-zero constant. The easiest way to fit this sort of square peg into a round hole type thing is to try and make it look like what the quadratic formula can accept. So we'll turn this into 2x squared plus 3x minus 4 equals 0. And here, the quadratic formula applies. It did not at the start, but it does now, with a equals 2, b equals 3, c equals negative 4. So I get that x is negative 3 plus or minus square root of 3 squared minus 4 times 2 times minus 4. 2 times 2 there. So I get minus 3 plus or minus the square root of 9 plus 4 times 4 times 2, 32. And then 4 down here, so minus 3 plus or minus the square root of 41 over 4. And there's no way to really simplify this further. Okay, so again, I think this would have been really hard to try to guess from factoring that these were the solutions. I mean, they're irrational numbers, right? This square root of 41 is a very complicated object compared to, say, whole numbers. So in these cases, I think that the quadratic formula should be your go-to way to solve quadratics. It's something that you should just commit to memory for the CLEP, and hopefully for the rest of your life. It's a really nice thing, I think, to understand.